Right. So let's see, everyone is here now. 2 people are missing. Any questions from the last time? So last time we discussed the expansion around a regular singular point, right? And I just remind you again, so the main conclusion was that so near a regular singular point, first of all, the first step you do is to find the indicial equation. Yeah, indicial equation is very important. That's one of the first steps you have to do. So indicial equation, and it will have 2 roots, R1 and R2, right? Okay, and we'll always arrange it in such a way that real part of R1 is greater than or equal to real part of R2. So that is just calling, giving it a name. Whichever real part is greater, I call that as R1. That's the thing. And then we saw that there are the 2 solutions. So the first solution for corresponding to R1, first solution is of the form Z minus Z0. So Z0 is the regular singular point, Z0, to the power of R1 times a series expansion where n goes from 0 to infinity. And these Cn's are determined uniquely in terms of C0 by the recursion relations, right? So that is one thing. And we also saw that this is convergent, etc. In fact, uniformly convergent within some radius. The second solution, now that depends. Okay, so there are several possibilities. If R1 minus R2 is not an integer, then the second solution is again of the same form, except that R1 is replaced by R2, and then you have again n equal to 0 to infinity with some different coefficient C tilde n Z minus Z0 to the n. That is when R1 minus R2 is not an integer. The subtlety arises when R1 minus R2 is equal to some integer n. N is some integer. Okay, this is going to be a positive integer because by assumption, non-negative integer, right? Because real R1 is greater than or equal to real R2. So this will be some non-negative integer. Okay. In this case, the solution is generally of the form again Z minus Z0 to the power of R2, again n equal to 0 to infinity with some other coefficient, I don't know, C double tilde, let's say, and Z minus Z0 to the n, plus some constant again, some constant times log Z minus Z0 times U1. So let me call this as U1, U1 of Z. So this is times U1 of Z. So the second solution U2 is of this form. So again, let me just give a name to this. This is U1Z and this is U2Z. There are 2 fundamental solutions. So this constant sometimes can vanish, but that will be a very special case where this constant vanishes, right? Generally, this constant will be there. So that is the general solution. Okay. One more thing I should mention here is that, which I will use for the hypergeometric equations, is that suppose that one of these happens to be an integer. Okay. Say either R1 or R2 happens to be an integer. Okay. In that case, okay, there are 2 possibilities. Either R1 is an integer or R2 is an integer, or both are integers, right? That's a possibility. So there are 2. If any of them is integer, then there are 2 possibilities. Either R1 is integer, 3 possibilities actually. Is R1 is integer, okay, in which case immediately you find I mean, this solution will have, of course, R1 being integer. So it will be meromorphic. There won't be any branch cut, right? Because this will be integer, that's anyway integer. So this will be some kind of a Laurent expansion, right? And in particular, if this integer happened to be positive, I mean non-negative, then we'll have an analytic solution, right? So one solution will be analytic. Integer, then it is a meromorphic. Then U1 is meromorphic. And in particular, and if R1 is, if this integer is positive, non-negative that is, then it is an analytic solution. Second possibility is that R2 is an integer, but R1 is not an integer. Okay. In that case, obviously, R1 minus R2 is not an integer, right? So in this case, so this U2 solution will be meromorphic now. You see, I'm saying that if R2 is integer but R1 is not an integer, then the difference between these two is obviously not an integer. So we are in this class, in this category, in this situation, right? So, sorry, this is U2. What am I saying? No, this is U1. Sorry, yeah. This is U1 and that's U2. Okay, so in that case, U2 will be meromorphic, right? And again, so in this case, U2 will be meromorphic. And once again, if this integer happened to be positive, I mean non-negative, then it will be analytic, right? And if integer is non-negative, if R2 is non-negative, then it's analytic. So that's the thing. And finally, the last possibility is both of them are integer. R1 and R2 both are integer. But in this case, okay, the U2 solution may have problem, may have logarithmic branch cut. I mean, that, as I said, depends on the details, whether this constant vanishes or not. But generally, you would imagine that this will not be 0, generically. And in that case, U2 will have a branch cut. But U1 will again be meromorphic, right? And once again, if that integer happens to be non-negative, it will be analytic. So that's the important point to see. If there is any of the roots of the indecent equation is a positive, I mean non-negative integer, then there is an analytic solution. Then one of the solutions is at least analytic. That's the important point. Yeah, we will. I mean, this will come. We'll come to this such situation when we discuss the hypergeometric equations. Okay, so now let me go to the towards the end. I mentioned about this equations. Okay, so you see, so what has happened now? I mean, our general equation was d2u by dz2 plus p du by dz plus q u equal to 0, right? And then we looked at, I mean, first before we discuss this, we first looked at the situation where p and q are analytic around some point, z0. And in that neighborhood, we were able to construct the fundamental solution, the fundamental set of solutions, and both of them were analytic, right? So around the points where p and q are analytic, the solutions also, both the fundamental solutions are analytic. Then we analyze a situation where where we are looking at a point z0 where p and q have at most first and second order poles, right? Which means regular singular point, right? And then we found these two fundamental set of solutions. But as you can see that all the solutions are local solutions. So give me a point which is analytic, where p and q are analytic, then I can produce to you in some neighborhood a fundamental set of solutions which are analytic. Similarly, give me another point which is a regular singular point, right? Then again in that neighborhood I can construct this fundamental set of solutions. But now we can ask the question of globally. I mean, give me some p and q. Okay, this p and q may have several singular points, right? Regular singular points, or even irregular singular points. Who knows, right? And many points where there are analytic, right? So around these points, I can start making, in each patch, I can construct these local solutions, right? So now we'll discuss more global, in the entire complex plane. Yeah. Yeah.
If R1 minus R2 is not integral, you can use R1 also.
Sorry, if
R1 minus R2 is not integral, you can use for the solution U2. You can use Z minus R2.
yeah, I mean, so you're looking at this case, R1 minus R2 is not an integer, right? In this case, for example, R1 minus R2 is not an integer. Yeah, R1 minus R2, yeah.
You can use R1.
No, we want to construct fundamental set of solutions, right? So U1 is always there, right? The question is U2. About the U2, you have two possibilities, right? So U1 is always there. U1 is always of this form.
For the first possibility, you can use Z minus Z not raised to R1. Because we will have no choice to R1 for the exponent to vanish.
No, maybe I don't understand. So sorry, are you saying that, say, R1, so you are saying R1 minus R2 is not an integer? Huh? And
Expression of U2,
yes.
you can use R1.
You mean to get the C tilde ends? Is that? Yeah. You can use the same recursion relation that we had generally obtained, right? Remember, we obtained this. I forgot now the equation. Okay, let me see this equation. So you can use either way. You can use either the Wronskian method. I mean, the variation of parameters, or a method of variation of parameters. Either you can use that way. So first you find the U1, and you can use the method of variation of parameters to determine the U2, right? Or you can directly just plug in the recursion relation which we use to solve for the CNs. The same recursion relation you can use for this solution also, except you replace R1 by R2. Yeah. Both will give the same answer. True. Yeah, that was a question, right? Yeah, okay.
Sir, do we have a situation where R1 and R2 are purely imaginary?
You can in principle have, yeah. I mean,
and then, so this one is just the real part of R1 minus R2 is when very part of R1.
Real part of R1. Okay, in that case, real part of R1 is equal to real part of R2 equal to 0. So you can just call any one of them as R1
So
and R2.
just for the real part, I think it should be otherwise.
Well, I mean, no, this is R1 minus R2 is itself is an integer. Yeah.
Okay.
Yeah. Which means the imaginary parts cancel. Imaginary part has to be equal. So I mean, if R1 minus R2 is R1 is in general complex, R2 is in general complex, right? So when we say the difference between them is an integer, that of course means the imaginary parts must be equal, or the two, right? And the real part, difference of real part is integer.
What if the real part is 0, but the imaginary part is equal?
If the imaginary part is equal, imaginary part is equal. Is it possible?
Because in general, P and Q are complexes, so
Sure. You can, yeah. So, for example, let's say you're saying, suppose the indicial equation is something like R minus I whole square. Is it possible? So then, but then we are again in this class, right? Sorry, in this class, because R1 equal to R2 equal to I, right? So R1 minus R2 is 0. Okay, in that case, it just happens to be 0, right? So you'll be in this case. So one of the solution will be U1. You choose one, call any one of them as U1 as R1, and then, but the second solution will have a logarithmic term. And we saw that, in fact, when capital N is 0, I think this constant is never 0 actually. So there will be a logarithmic term. I think at least in the example we gave, there were two coincidental roots, and yeah, I think it's impossible that constant would vanish if capital N was 0. Yeah. All right. So now let's. So these kinds of equations where the P and Q have only regular singular points in the entire complex plane, including the point at infinity. Those equations are called Fuchsian equations. It's after a mathematician's name, Fuchsian equations. So these are the equations where PQ have only only isolated regular singular points. Including infinity, and that's important, including infinity, including the point at infinity. Remember when we said when you include the point at infinity, the complex plane together with the point at infinity is topologically a sphere. So we are saying that this equation is well defined on the sphere itself, so including the point at infinity. And so these are Fuchsian equations, and they have isolated regular singular points. Okay, so of course outside these regular singular points, the P and Q are analytic. So most of the places is analytic except for some isolated regular singular points. So that's a kind of Fuchsian equation. And in particular, we'll actually focus on the situation where we have only three regular singular points. I mean, in general, Fuchsian equations, you can have any number of regular singular points. It doesn't have to be 3 or 2. It could be any number, 10, 20, whatever, right? But those equations become extremely messy, difficult to solve. So we'll look at this 3 regular singular point, and that already gives you a very large class of interesting solutions. This is called the hypergeometric solution. The resulting equation that you get is called hypergeometric equation, and the solutions are called hypergeometric functions. And we'll see that many of the functions that you come across usually in the mathematical physics are either hypergeometric functions themselves or related to hypergeometric functions. So that's why the study of this is very important. Okay, so let's first write down. So let's suppose these singular points are Z1, Z2, and Z3. These are the 3 regular singular points. Okay. So let's try to write down the most general expression, the most general second-order differential equation, which involves only 3 regular singular points at points Z1, Z2, and Z3. Okay. Now I'm going to make a claim. Perhaps, yeah, maybe I can erase all this and start from there because this will require the entire blackboard. So remember, these 3 points are Z1, Z2, Z3, where we have regular singular points. So the claim is that the most general such equation can be written in this way: d2 u by dz2 plus okay, now some constant divided by z minus z1. Okay, so some constant, this is a constant. I will parameterize this constant in a convenient way, but at the moment it's just some constant. Okay, plus another constant divided by z minus z2 plus another constant divided by z minus z3. Okay, so because remember, see, P, this is P. Let me put it like this: du by dz. Okay, now see that this. This is just saying that the P has a first order pole, right? Of course, it may happen that the P doesn't have a first order pole at Z1. In that case, this constant would be just 0, right? But generally, this constant will basically tell you what is the residue at the Z equal to Z1 for the P. It may be 0 or it may not be 0. Similarly at Z2 and Z3. But of course, you can say, why is it most general? Why couldn't I add any analytic function, even for another constant, for example, let's say some constant c, why couldn't I add such a constant, right? This has no problem. This is analytic everywhere, right? Or in fact, more generally, any analytic function, but analytic in the entire complex plane, right? I could in principle add that. It has no problem. Problem is at infinity. You see, you want to make sure that at infinity there is no singularity for the P and Q, right? That is what fixes this thing to be 0. There is no other choice. Okay. And how do you see this? I mean, I still have to write the Q, but for the moment, let's just already focus on this. How will I look at the infinity? So to study at infinity, I just have to do the inversion, right? Write z equal to 1 over z prime, and then study what happens when z prime equal to 0. But when you do that, I have to make the change of variable, right? So in particular, d by dz becomes d by dz prime over dz, but z prime is equal to 1 over z, which means, so this is 1 over d of 1 over z by dz, that gives you minus 1 over z square, okay, minus 1 over z square, but minus 1 over z square is the same as z minus z prime square, right? Because I want to write everything in terms of z prime times d by dz prime. Okay. So now let's see what happens to this second order derivative. So this will be there are two such each of this d by dz is replaced by that, right? So you get here, okay, minus minus becomes plus. So you get here, so d2 by dz2 u is the same as z prime square d by dz prime, z prime square d by dz prime u, right? So let's simplify this. So here you have two terms. This one acts on that, or this one acts on that. When it acts here, you simply get z prime to the 4 d2 by dz prime square u, and when it acts the other one, you get 2z prime, so 2z prime cube d by dz prime u. Yes. So this will become that, but you remember, I mean, when we study this equation, we make this coefficient 1, right? So which means I have to divide this entire equation by z prime to the 4. Okay. So if I take it out, if I can just write, take this out. So then this becomes 1 over z prime here, right? Okay. So that becomes 1 over z prime. Okay, that's not the whole story. Of course, I have to also look at this. So this is the, say, p. So what about that term now? So we have a term which is p du by dz, which is the same as, so p of z. So I have to just, becomes p of 1 over z prime, right? And then this minus z prime square d by dz prime u. So putting these two things together, I mean, already you can see that when I put them all together, since I have to take out z prime to the 4 as a common factor, so putting these two things together, you get z prime to the 4 and then d2 u over dz prime square plus 2 over z prime. And then from here, I have to take out divide by z prime square. So you get here minus p of 1 over z prime over z prime square. This whole thing is multiplying du over dz prime. Okay, and this should have no singularity at all at z prime equal to 0, because we are saying infinity is a regular point. I mean, it's an ordinary point. There is no singularity there. So in particular, for example, so suppose I had, for example, added a constant here. No, okay, so first let's look at what happens with this. I replace each, this is p. Okay, let me put here some f of z. This is p, I just replace z by 1 over z prime, right? And see what happens when z prime goes to 0. So this is the same as, so I can take it up. So this becomes z prime, I mean this constant, whatever that constant is, divided by 1 minus z prime z1, right? So this, you see, this gives you a z prime in the numerator. I mean, z prime goes to 0 limit, I can forget that, no? So it becomes z prime. So these three terms go like z prime, and because it's the same thing here also. So these three terms go like z prime. So that z prime will cancel one power here, so you get a 1 over z prime, and then you can hope to cancel these two between these two terms, right? So that will in fact impose some conditions on that. But now suppose I had a constant here. Just imagine there was a constant. Then that is not going to provide this z prime. Okay? You say constant. I mean, nothing happens when you replace z by 1 over z prime. That constant remains that constant, right? So that constant will give you a second order pole. And what can you cancel it with? No. So that's why you cannot add, similarly, suppose I add a power of z, right? That's even worse because this will becomes 1 over z prime. So this p will have an 1 over z prime cube, this term, right? So there's no way I can add anything else here. Okay? So the best I can do is this. Okay? And now, but still I have to make sure that the 1 over z prime term from here cancels between this and that, right? And so I will parameterize. This is a useful parameterization. You will see why it is useful. These are three constants, right? So I will parameterize the constant like this: 1 minus alpha prime. These are all constants. This is a parameterization of that constant, nothing more. And 1 minus beta prime, and 1 minus gamma prime. Okay. Now let's look at that here. So in z prime goes to 0 limit, each of these things I can ignore that. So this gives you z prime times that constant. This gives you z prime times this constant plus this gives you z prime times that constant. So this whole thing together gives you z prime 1 over z prime, because z prime divided by z prime square is 1 over z prime, times the sum of these three constants, right? The sum of these three constants, which is the same as 3 minus alpha prime minus beta prime minus gamma prime, and that all that must cancel from here. Cancel with this. I mean, there is a minus here outside, so there is a minus here, and there is a 2 here. Okay. So what the equation that we get is 2 minus 3 plus alpha, etc. This should be equal to 0. So that implies, so the condition that you get is that alpha prime plus beta prime plus gamma prime should be equal to, you see, okay, this minus, so that this all plus, but here you have minus 3 plus 2. So it's minus 1. That sum must be equal to 0. So that tells me that this must be equal to 1. So this is the basic relation between these constants. Okay. So that's already so that's what I'm saying. This the most general expression. There's nothing else you can do. The requirement that infinity is an ordinary point, I mean, is analytic. That imposes a very, very strong condition, you see, on the p, right? First of all, it fixes this, it gives a one relation between these three constants, right? And secondly, it tells you that you cannot add anything here, right? That is, so you see, the freedom to add an analytic function here, there are infinite number of analytic functions, right? Any Taylor, any power series with the positive powers of z, right? That so there are infinite number of freedoms here, but all that is removed by requiring that at infinity you should have a ordinary point. Okay. Now finally we have the q term. So again I will. No, I think that's, yeah, sorry.
So if z equal 1 over z.
But then it is not, right? Because that, then you have another singular point, right, at z equal to 0.
If z equal,
say 1 over z, right? But then you have four singular points. I'm saying that we have only 3 singular points, z1, z2, and z3, nothing else. Huh? Okay, if you have 4 singular points, yeah, then you have, say, at z equal to 0, right? Then there would be, z minus z4, for example. No? Then that will be, then again you will have, there will be some relation between these 4 constants, right? Basically it says that the sum of those 4 constants must be equal to 2. That's what it is saying, right? So it gives you one relation. But yeah, so we are looking only at three regular singular points. Okay. Now, finally, we have to we look at the Q. So Q again, the most general. Remember, Q can at most have second order poles at these points, right? That is the definition of regular singular point. So I can always write Q in the following way: 1 over z minus z1, z minus z2, z minus z3 times. Now I write it here. So what is that? Yeah, z1 minus z2 times z1 minus z3 alpha alpha prime divided by z minus z1 plus so now just I mean cyclically change these indices. So z2 minus z1 z2 minus z3 divided by z minus z2 times beta beta prime plus z3 minus z1 z3 minus z2 divided by z3 minus z minus z3, sorry, times gamma gamma prime. This whole thing is Q, so Q this times U. So that's a full differential equation. Okay. So once again, you have to. So I mean, what you have to do again. Okay, first of all, you see that this has a right property, right? This is at most second order pole. If you focus on z equal to z1, it has at most second order pole, and then when you multiply this with that, it will have first order pole at z1. So second order pole and first order pole at z equal to z1, and same thing happens for z2 and z3. Okay, I mean this multiplying that will have first order pole at z2, but this multiplying that will have second order pole at z2, right? Actually, it's not just second order pole; you have to expand. So, right. So there will be, but the important point is the Laurent expansion around each z1 and z2 and z3 can at worst have second order pole and then first order pole, then regular pieces. Okay, and once again now, if you make the, I mean z goes to 1 over z prime, and remember I have to divide by z prime to the 4, right? Because I mean. I have to factor out this thing and then examine what happens to, I mean, that's how you define P and Q after dividing by this quantity, right? The coefficient. So I have to take this entire thing, replace z by z prime, 1 over z prime, and also divide by 1 over z prime to the 4. Yes? So that is going to give you a lot of conditions, right? So you have to cancel all of them, 1 over z prime to the 4, 1 over z prime cube, 1 over z prime square, 1 over z prime. So there are lots of conditions you have to cancel because you don't want any singularity for Q at z prime equal to 0, correct? So for example, let's see, if I replace z by 1 over z prime, then you see that this 3 gives you, I mean, each of them will give you z prime, z prime, z prime, right? So you get here z prime cube from here, and from here you get z prime to the 4. I mean, one more z prime here. So you see that's the reason why you need this. So essentially, what we are saying is that each term, you see, each term has a property that this is z, 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 and there is another z, z to the 4, right? So, and we are looking at z goes to infinity limit. So 1 over z to the 4 goes like z prime to the 4, right? Which you exactly needed to get rid of this thing. So that's if there was any term which didn't have, which had only 3 powers, not the 4th power, okay, then you would not have. You would have only z prime q up, right, and which would not be able to cancel 1 over z prime to the 4. So you would start getting pole. That is why you see the way we have arranged it. Each term has exactly each term has 4 factors of this 4z, and that is precisely to cancel that. And that's the most general expression. You see, I mean, you cannot. So now you see that here. Now you may say, why? I mean, I have this. This is some constant. I mean, this is any constant, and another constant, another constant, right? But what have I done? So, I mean, to begin with, we have basically, let's see, one constant here, one constant here, one constant here, right? subject to one condition, that condition being that the sum of those coefficients cancel these two, right? So there's one condition here, and here I have three constants, right? So let's say even forget this condition for the moment. So I have three constants here and three constants here. Okay, I've just chosen a particular parameterization to write it in terms of this alpha and r. So here you see you have 6 constants, right? So this is just a convenient parameterization. It's nothing more than that. Okay, you could have written in principle just some constants C1, C2, C3, C4, C5, C6. Okay, with the condition that C1 plus C2 plus C3 is equal to 2. That's fine, right? But I'm saying that I'm just choosing this particular. I'm calling C1 as 1 minus alpha prime, and this C4 as this times that times alpha prime, right? That is no problem because I have two parameters here, C1 and C4. I'm expressing in terms of, again, two parameters, alpha and alpha prime, right? That's all. Z1, Z2, Z3 are fixed, right? Because those are the positions of the singularities, right? So I have two constants. I've just traded them with two constants, alpha and alpha prime. This is a parameterization. You'll see immediately why this is a very convenient parameterization. Because actually what it will be, this alpha and alpha prime will directly be the roots of the indicial equation. Okay, that's the reason for this parameterization around Z1. Similarly, beta and beta prime will be the roots of the indicial equation around Z2 and so on. So that's the reason for this parameterization. Okay, we'll see. But is that clear? You see, I mean, see, once again, you see that this requirement has restricted to just these three terms. You cannot have anything else, you see, because we said we need 4 factors of this. So that's the only thing you can do, right? Anything which is less than 4 factors will have singularities once you divide by z prime to the 4. Okay. So infinite number of possible terms that you could have put here, I mean, any analytic function of z and so on, all those things are removed. So it's a very strong requirement. The regularity at point, I mean, holomorphicity at analyticity at infinity is a very, very strong condition. So this is the most general equation. So now let's study the indicial equations, okay? Because that's the most important first step in solving anything here. So I mean, to just remember, I have altogether I have 9 complex parameters here. After all, Z1, Z2, Z3 are also parameters in the right, the positions of the thing, and similarly, all these are complex numbers. So you have to begin with 9 complex parameters, subject to one condition. Subject to one condition. Actually, this is one complex condition, of course, right? These are complex numbers, so I have to separately equate the real part and the imaginary part, right? So basically, so there's one complex condition. So really, you have actually eight free complex parameters. Okay, that's. But we will eventually reduce this number of parameters. I mean, many of these parameters are redundant. Okay, we will see later on in a short while. Okay, so now let's study the indicial equation. So let's expand around Z1. So expand the U in power series around Z1. So we are looking at Z minus Z1 to the power of R, and then you have some series expansion. Okay, so let's plug that in here. So you see that what is the indicial equation? So you remember the equation was R times, what was it? R square minus 1 minus A0 R plus B0, right? Plus or minus? Plus B0. This was equal to 0 was the equation. Now what was the A0 and B0? A0 was the coefficient of the first order pole of P at Z equal to Z0. Z1, in this case Z1, and B0 is the coefficient of the second order pole of Q. And that's easy to read off from here, right? So from here, the first order pole is this, at Z1 is that. So the coefficient is simply, so A naught is simply 1 minus alpha prime. Okay. And what about B naught? So B naught is the coefficient of the second order pole at Z equal to Z1, but that is this that can only appear from the product of this with that, right? But when I do this, so I have Z minus Z1 square, but then I still multiplying with some function of Z. So to extract the coefficient, I need to then substitute Z equal to Z1 in the remaining things, right? I mean, you see, what is Q? So Q is, let's look at this term. It is Z1 minus Z2 times Z1 minus Z3 alpha prime divided by Z minus Z1 square. I'm looking at the first term, times Z minus Z2 times Z minus Z3. Okay, plus other terms, but those terms can never give you second order pole, right? This and that at Z1, right? So only second order pole can come only from here. So then the lower order poles, lower order poles. But even here, you see, near Z equal to Z1, I have to make a Taylor expansion of this part. This is analytic. This part is analytic at Z equal to Z1, right? So the leading term comes when you just substitute Z equal to Z1 here and here. But then this cancels exactly that. That's the reason for parameterizing like this. So then these two cancelled, then the coefficient is simply alpha prime, right? So B naught is alpha prime. And now you see, you just plug that in here. So 1 minus A naught is alpha plus alpha prime. So this becomes alpha plus alpha prime, and that is alpha prime. And then clearly the roots are r equal to alpha and alpha prime, right? So the two roots are r equal to alpha and r equal to alpha prime. So you see, it's just a convenient way of parameterizing those constants, so that you can, by looking at the equation, you can read off the indicial, the roots. That's the only reason. And it's clear the same thing will happen if you would expand around Z2. It will be this term, and that term will be the crucial things. And again, the two solutions will be beta and beta prime, and at Z3 it will be gamma and gamma prime. So these numbers are just the roots of the indicial equations. 3 points. So there's now, is there any question on that, on this point? I mean, so in other words, here, this will start with the coefficient of Z minus Z1 square is when you substitute this by Z1, so this cancels. So you get here alpha prime, and then lower order poles. That's no. I mean, if I want to compute this coefficient, what I can do? I can multiply this q by Z minus Z1 square, and then take Z equal to Z1, right? That's an easy way of doing it. When you do that, when you multiply by Z minus Z1 square, this cancels, and then whatever remains, you substitute Z equal to Z1, and in which case this cancels. Is there any question? No? Yeah, there's. Yeah. Sure. That's what I said. I mean, this is completely symmetric expression, right? So when you do expand around Z2, this A naught will become 1 minus beta prime, and B naught will become just beta prime, and so on. So. Okay, so now I just introduce a symbol. There's a symbol. The solutions of this equation is I mean, this is just a symbol. This is called Riemann P symbol. Riemann P symbol. It is convenient. I mean, this Riemann P symbol is denoted like this. There is a P of, because I mean it's clear that this solution of this equation is entirely determined by these parameters, right? These parameters alpha, alpha prime, beta, beta prime, gamma, and Z1, Z2, Z3 be determined by that. So you just have this symbol captures those constants, those parameters. So you write it like this: Z1, Z2, Z3. So these are the three singular points, and then below the singular points you just write down the roots. Roots of the indecent equation at point Z1, at point Z2, at point Z3. So here we have alpha, alpha prime. Here you have beta, beta prime. And here you have gamma, gamma prime. And then you just put also Z. Meaning, after all, this whole thing is a function of Z. Solution, whatever U will be a function of Z. Right? So U will depend on the Z because it's a function of Z. But of course, the solution will depend on these parameters. Because the differential equation changes as you change these parameters. So you will depend on these parameters as well as a function of Z. Right? So this is just a symbol, because by looking at it again, you don't have to write this long differential equation. By looking at this, you immediately say, okay, this is a solution of a Fuchsian equation with three regular singular points, and the roots of the indecent equations are this. So that's it. You don't have to write all this long equation. This captures everything. Okay. So now, as I said, I mean this is too cumbersome because you have to handle these 9 parameters, subject to one condition, but nevertheless, it's too many things are written here, right? So what we will find is there are certain symmetries, and using those symmetries, you can actually reduce the number of parameters to finally just three parameters. You'll be able to reduce it to. Okay. So you see that this equation has some nice properties. Okay, it has some nice property in the following sense. There are two transformations. One is this is something I never mentioned to you, I think, right? That was a part I skipped, conformal transformations in the second chapter, right? But okay, let me just, I mean, we don't need too much details about that, but consider such a transformation. Z goes to Z prime, I make a transformation, where Z prime is given, Z prime of course is a function of Z, but it will be a particular type of function, and I will use the same A Z plus B divided by C Z plus D. I don't know, did I ever talk about that? I talked, okay. Yeah. Very briefly, maybe, very briefly, I think I talked about it. Yeah. No, it was very brief, I think. So consider this. So what it does. So let me say here is my Z plane, and here is my Z prime plane. Okay. So this equation Z prime equal to AZ plus B over CZ plus D obviously gives a rule of mapping. Give me a point here. Just plug that value, the value of this complex number here. This is going to give me some complex number, and that will be some point here, right? So it will be a map. So this equation gives me a rule to map the points in the Z plane to points in the Z prime plane. Okay. Now the important point about this map is that this is a one-to-one map. So you can also, I mean, this rule gives me, give me a point here, and I will tell you what the point is there, right? But it's also other way around. Give me a point here, I can tell you what the point is here. And that you can do, you just have to find the inverse relation, right? Okay. So solve Z in terms of Z prime. That's all you have to do. So you can do that, multiply by CZ plus D. So CZ plus D, Z prime equal to AZ plus B. And now collect all the linear terms in Z. So that becomes CZ prime minus A times Z equal to B minus dz prime, right? And therefore Z is equal to B minus dz prime divided by CZ prime minus A. So give me a point Z in the Z prime plane, and this formula, I can use this formula to tell you what the point in the Z plane is. So the important point of this map is it's a one-to-one map, you see. So I mean, in general, it could happen that you know, a map is not one-to-one, right? For example, if I take z prime equal to z square, this is certainly not one-to-one map, right? Z equal to +1 and z equal to -1 are mapped to the same point, z prime, right? So this is not a one-to-one map, but this is a one-to-one map. That's the important point. Huh? Yeah.
From here, when we take each point of Z plane, every point I'm not taking.
Yeah, every point. It gives you a map. So I'm saying that this is a map.
If Z is equal to -d/.
Good. That is the next point. Yeah, good. I mean, that's the point here. You see, this, so what I'm saying is this map is one-to-one, but it is not a map from the complex plane to complex plane. It is a map from the complex plane plus infinity to complex plane at plus infinity. You see, this is not a map from complex plane to complex plane. Why? Because of precisely what you are saying. What happens if z equal to -d/c? Then z prime is infinity, right? Similarly, what happens if z prime is equal to a divided by c? Then z is infinity. So the particular point, so this z equal to, so this is special point which is -b/c, right? This is some point in there. Now that is mapped to the point at infinity here, the z prime. Similarly, in the z prime plane, if you take some a over c, this is some a over c, some point, this is mapped to point at infinity here. I don't know, how shall I call this, a point at infinity here, okay? So it is not a map. If you just if you say that I don't include the point at infinity, then this is not a well-defined map, right? But if you include also points at infinity, which is what we are doing here, you see in this analysis, we are also including the point at infinity. We are making sure that things are well behaved at point at infinity, right? So when you have included the z plane together with infinity and z prime plane together with infinity, then this map is well defined and is one-to-one, okay? So that's a crucial point here, that infinity has to be included there. Okay. So what I could do, I mean, so you see I have now several parameters here, right? A, B, C, D. Actually, you may say there are 4 parameters here, but really not, you know, because I can divide A, B, C, and D by same complex number, and this equation doesn't change, right? Suppose I divide some I don't know, some E, let's say. I can take A goes to A divided by E, B goes to simultaneously B divided by E, C goes to C divided by E, and D goes to D divided by E. See, nothing happens to this because 1 over E comes from the numerator, cancels with the 1 over E. So really it's not 4 parameters, actually 3 complex parameters, okay? Because by using this E, I can, for example, always set one of them equal to 1, right? So it's really 3 complex parameters. So I can use these 3 complex parameters to get rid of, this Z1, Z2, and Z3, or more appropriately, to put Z1, Z2, Z3 at some fixed points, okay? Some convenient point. For example, the convenient point would be I can choose Z1 equal to 0, for example, Z2 equal to 1, and Z3 equal to infinity. Right? I can, by choosing these parameters A, B, C, D, I can move this point Z1, Z2, Z3. So Z1, Z2, Z3 are 3 points here, right? Some 3, who knows what points, but whatever. Z1, Z2, Z3 are 3 points in this complex plane. Okay. Now under this map, each of these points will go to some points here, Z1 prime, some Z2 prime, and Z3 prime, right? So this point is mapped there, this point is mapped here, and finally this point is mapped here. Yeah, but precisely what these points are will depend obviously on the choice of A, B, C, D. Yes, I can choose conveniently A, B, C, D in such a way that, for example, I set Z1 prime equal to 0, Z2 prime is equal to 1, and Z3 prime infinity, right? So I can get rid of basically what I'm saying is that I can get rid of these 3 parameters and fix them to some convenient value. So they're not, that is one thing. Okay, I need to of course show to you that I need to show to you that this under such a transformation. Okay, so now I go to in the Z prime variable, this equation remains the same type of equation. Nothing, it doesn't change. is the same type of equation. So that one has to check. I mean, in some sense, it's guaranteed, right? Because, okay, this second order differential equation will again go to some second order differential equation, right? Which will again, I can rewrite it in terms of some p prime and q prime in the new variables, right? Once I once I make the coefficient of this second order term as 1 by suitably dividing, right? Like what we did for the inversion. When we analyze what happens at point at infinity, after all, that was just one special case where I had chosen a equal to 0, b equal to 1, c equal to 1, and d equal to 0. That was the inversion, z prime equal to 1 over z. That was just a special case of this. This is a more general case. Okay. So in all of these cases, I mean, nothing should happen, because after all, I've already ensured that in the original z plane, I have only 3 poles. I mean, 3 regular singular points. All the other points are, I mean, p and q are analytic in all the other points. So when I make such a transformation in the z prime, again, I should have 3 regular singular points, no more. But you can explicitly check it also by just applying this. Before I was doing z prime equal to 1 over z, but now I do the same thing with this transformation. You know, you change, write everything in terms of z prime variables, okay? And you will see that the equation goes back to the same form of equation, okay? Except that, so let me just write it. I think I will not do this calculation here because it will take just a long time. There's nothing deep about it. It's essentially the same as what we did for the inversion, but slightly more complicated because now the form is more complicated here, right? So if you change the variables. So use this. So change the variable. I mean, so let's see. What is d by dz is d by dz prime, and then dz prime over dz. But dz prime over dz, you can compute what it is. It's so this is equal to cz plus d square, and then you get here a times cz plus d minus az plus b times c times c. So you see that AC, I mean the z term cancelled. Okay, I mean ACZ cancels the AZC. So what is left over is AD minus BC, and in fact, okay, they don't say, but you see, I can, using this freedom of E, I can always make the AD minus BC equal to 1, right? I can, using this freedom of E, right? I can, to simplify, so I can always choose AD minus BC equal to 1 by using this freedom. Okay, so that the numerator simply becomes 1. I mean, just to simplify. So that becomes 1 over cz plus d square. So this is 1 over cz plus d square, d by dz prime. Actually, you can again now express this back in terms of z prime by using this equation. Okay. Okay, it will require, maybe I could have done it here first. So this is the same as 1 over c times this guy. So what is cz plus d? Cz plus d is, using this equation, you get here c times b minus d z prime divided by cz prime minus a plus b times cz prime minus a. Right? So now you see again the z prime cancels, and what is left over is again cb minus ad, but that is minus 1. So this is simply minus 1 over cz prime minus a. Okay. So, sorry? Yes. Yeah, I mean, yeah. I mean, suppose AD minus BC was some not equal to 1. Let's say some f, let's say. I just divide this by root f, everything, right? This f is some constant, complex number. Right? And then just call this as a, and that is d. Actually, even that is not necessary. I mean, you don't need to even do that. You can just keep it, except that you have to keep track of this constant. that's okay. So okay, so you see that this is what you get. So the expression is, this is simply minus 1 over cz prime minus a d by dz prime. Now just substitute that. So d by dz square will become square of this operator, and so on. You keep going through all that, and and then rewrite everything in terms of z prime. Okay, and then you will see. So what you will see is that at the end of the day, you will find an equation exactly like this. It's a long exercise. I mean, but nothing deep about it. It's just mechanically, just churn the machine, and you'll get that. So d2u over you'll get d2u over z prime square, and then you will find exactly the same type of objects. In fact, the same bracket. So 1 minus alpha prime over now z prime, right, minus z1 prime. And what is z1 prime? Z1 prime is simply az1 plus b divided by cz1 plus d, which is exactly where the z1 is mapped to, right? And similarly, all the remaining stuff is just all these replaced by primes. And similarly here also, all these replaced by primes. That's what you will end up. Okay, so it will require 2 or 3 pages of going through the systematically but it's nothing. It's a very simple but tedious. It's all. It's not. So what does it mean? It means that with such a transformation, with such this is called fractional linear rational transformation or something like that. So this transformation, which is called the conformal transformation, z prime equal to az plus b divided by cz plus d, I can change this equation to exactly the similar equations, but now these are replaced by primes, right? So this tells me that under such a transformation, you will take the Riemann symbol z1, z2, z3, alpha prime, beta prime, gamma prime, z to this will map to p, just z1 prime, z2 prime, z3 prime, alpha prime, beta prime, gamma prime, z prime. Okay, that's what. And now what is the use of that? Of course, as I said, the use of that is I can now fix these things. I mean, these guys I can fix to some particular values, right? So that I don't have to keep track of these parameters, right? The z1, z2, z3. I just fix them to 0, 1, and infinity. That's what the standard thing will be, 0, 1, and infinity. In fact, let's see what is the standard. They choose here. Yeah, they choose z1 prime. They choose, I mean, it's just a convention, it's nothing more. z1 prime equal to 0, z2 prime equal to infinity, and z3 prime equal to 1. Okay. You can always find capital A, B, C, and D in such a way that this is true. Okay, let me just, before erasing this blackboard, let me just do that to show you that indeed you can choose A, B, C, D such that is true. So, for example, let's say that z1 prime I want to be equal to 0, right? So we have equation 0 should be equal to A z1 plus B, C z1 plus D, right? This is z1 prime is equal to that. Now, z2 prime should be infinity. So infinity is equal to A z2 plus B divided by C z2 plus D. And finally, z3 prime is 1. So you have 1 equal to A z3 plus B divided by C z3 plus D, right? And I want to solve for A, B, C, D, right? I want to find if I can find an A, B, C, D such that these equations are true, right? So for example, let's see, what does this tell me? This tells me that this will be 0 if the numerator is 0, right? So B must be equal to minus A z1, right? And this infinity means that this must be 0, right? So that tells me that D equal to minus C z2, okay? And now let's plug that in this last equation. So you find here A1 equal to B is minus A z1. So substitute that here. So this gives you A times Z3 minus Z1, and the denominator is C times Z3 minus Z2 when you substitute this. So this tells me that, for example, this implies that C is equal to that. So this tells you, this defines everything in terms of A, because B is A Z1, C is this, A times this thing, and D is C, so C is this times that. So everything is determined in terms of 1. But that, of course, we knew that, I mean, the one parameter is, you can always set equal to 1 by that, using the fact that there is a freedom of dividing by the same number, right? So I can choose, for example, A equal to 1. So the point is that there's a solution to this. So I can take this, indeed, this choice, right? And making this choice becomes very simple because, see, if, now you see everything is replaced by the primes, no? So Z3 prime is, Z2 prime is infinity. So you see this just drops out, right? And one of them is, so this becomes 1 over Z, and that becomes 1 over Z minus 1. Right? Not 1, I mean some constant here, but this guy I can drop out. Similarly here, you see what term will survive here. In fact, yeah, just take Z2 equal to infinity. So from this guy drops out. Similarly here, here you see here this will be some, I mean drops out. I mean you can cancel this, right? Z2 goes to infinity. This guy will cancel with that. In this term, you have this. All of this together gives you just 1 because Z2 is infinity, right? And similarly here, I mean you can simplify. The expressions become very simple when one of the points is at infinity. Okay, that's the use of that. But there's one more symmetry, and that is, see, so far we said, I mean this symmetry, this transformation allows you to change these parameters. But we can also, there's another transformation which allows you to change these parameters also. And that is the following. But before that, before I erase this, is there any question here?
And I think to have the unique solution, you need 80 minus BC to be non-zero.
80 minus BC should be non-zero. Yeah, you're correct. Yeah. That's important. Yeah. Because I mean, if AD minus, if you see that, then I mean, if you think of this matrix A, B, C, D, 2 by 2 matrix, if AD minus BC is 0, the determinant, then this row is, I mean, they are linearly dependent, right? But that means that this becomes a trivial, this becomes a nonsense because this cancels out. You see, I mean, this implies that C, if AD minus BC is 0, then this is linearly dependent on that, right? So which means C is some constant, I don't know, I'm running out of constants now, say A times capital A and D equal to A times capital B, same A, right? Once you substitute that in this transformation, this whole thing cancels and you just get 1 over little a. But that is a singular transformation because all the values, I mean, Z prime is just a constant. It's not a map of any, I mean, it's a, no. So you have to avoid that. Yeah. Good point. You cannot allow this. This determinant must be non-zero. Okay. Yeah. This is. Yeah. This group. I mean, this kind of transformations. If you make successive transformations like this, right? I mean, you can do successive transformations all at the same time. Z goes to Z prime by this. Then Z prime goes to some Z double prime, which is again some linear function of Z prime divided by another linear function of Z prime, and so on. That forms a group in the sense that it closes. Okay, and that group is simply obtained by taking such matrices and multiplying these matrices, and that forms a group actually. I mean, I have not talked about group, but this is called GL2 group. And if you impose the condition that AD minus BC equal to 1, okay, because as I said, we can always make that choice, no? Then it becomes SL2 group. So this group is SL2, SL2C. C means it's complex numbers. These are complex numbers. So the SL2C group. That's an important point. SL2C group is the symmetry of sphere, two-sphere, because this is the complex plane plus point at infinity is a two-sphere, right? So this SL2C is the symmetry of the two sphere actually, it turns out. Okay, so now, so any more questions or comments on this? Because now I'm going to erase this and talk about the second transformation, which will allow us to change these values. I mean, you see, this one didn't change its values; it remained the same, right? Only these guys changed, positions changed. Now, okay, can I erase now? Okay, so let's consider now. Let's write u, u as this u is the solution of this equation, right? So I write u as z minus z1 to the power of r, z minus z2 to the power of s, z minus z3 to the power of t times some another function v of z. Okay. And let's just plug that in here. Okay. So this is the definition of v, essentially, right? I mean, I'm just so u I express it in this way, u of z, where okay v is some another unknown function, right? You can always do this. I mean, I'm not without losing any generality. I can always do that because that's the definition of v. V is u divided by all that, right? That's the definition of v. Now let's plug this entire thing in this differential equation. Then what I will get? I will get a second order differential equation for v. Okay, and let's see what kind of differential equation we get here. Okay, so this again requires this. Unfortunately, again, a bit tedious. I don't know whether I should. Yeah, okay, let's do this. Just it will require some time though. So let's take d by dz of u, because I have to evaluate this and I have to evaluate that, so there are several things to do. This is the same as z, so this prefactor z minus z1 to the r, z minus z2 to the power of s, z minus z3 to the power of t times dv by dz plus r over z minus z1 plus s over z minus z2 plus t over z minus z3, this whole thing times v. Is that, let's see, do you agree with that? So the point is the following. Okay, when I apply derivative, there are several possibilities. Derivative can hit here, 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 and here, right? When it hits here, you just get that. Now let's consider in other cases. When it hits here, you're going to get r, so r times this thing to the power of r minus 1. But since I'm taking out that common factor, this becomes r divided by z minus z1. Similarly, when it acts here, you get s divided by z minus z2, and so on. Okay. Now let's apply second derivative, d2u by dz2. Now it becomes a mess, but okay. So there will be so one term in derivative hits inside here. What shall I call? I mean, okay, let me write z minus z1 to the r, z minus z2 to the power of s, z minus z3 to the t, and then the derivative hitting inside here. So there will be several terms, d2v by dz2 plus then the derivative hitting here. So again, there are two pieces here, r over z minus z1 plus s over z minus z2 plus t over z minus z3 times dv by dz. And then I have the second derivative, I mean derivatives acting here. So that will be minus r divided by z minus z1 square plus s divided by z minus z2 square plus t z3 square, whole thing times v. Okay. So that is when the derivative is hitting here. But now when the derivative hits here, what am I going to get? It will be this whole thing times again this factor, right? So plus r over z minus z1 plus s over z minus z2 plus t over z minus z3, this whole thing times that whole thing, right, which is dv by dz plus again the same bracket T over Z minus Z3 times V. Okay, and then whole bracket closed. So that's what it is. Huh? So, sorry?
Here we have one factor.
Yeah, these two things will add up to give you a factor of 2. Yeah, correct. Yeah, yeah. There is this thing and that thing. Yeah, you can actually combine it. Shall I combine it already? Huh? I mean, just this term, this part, I can combine here because the same expression and with a positive. I mean, both are adding up. Shall I do that here? Just put here 2 and get rid of this term. Huh? No, you don't want. Okay, let me leave it as it is. Okay, let me leave it. Okay. I will do that when I combine everything. Okay. So now let's combine everything here. You see, this factor is going to come out from everywhere. The way I have written, you see, this will come with that. This factor, this whole thing will come with that, right? And of course here, because this is just directly u. U itself has that factor, right? So that factor is a common factor. And since at the end I'm going to make the coefficient of d2v by dz2 as 1, I have to divide by that, right? So I can just get rid of that term, that pre-factor, huh? Because that's common to each term. Is that clear? Am I? Huh? Yeah. Okay. So after getting rid of the common factor, then you find that d2 equation becomes d2v by dz2 plus, now let's look at the linear term, I mean the first derivative on dv by dz. So as we said, there are 2 terms, this and that. So it gives you 2 times r over z minus z1, let me write like that, 2r divided by z minus z1 plus 2s divided by z minus z2 plus 2t divided by z minus z3 times dv by dz. But also I have to include this term. After all, this is coming from the first derivative here. So dv by dz times this whole thing. Okay. So you see, maybe I should have written like this. First, let me write this term. Then I will add that other piece. So this term is z minus z1, and then here you get 1 minus alpha prime, plus z minus z2, 1 minus beta prime, plus z minus z3, 1 minus gamma prime. That is coming from here. I mean, this whole thing is multiplying dv by dz, right? Okay. So where it's coming from, I just plug this definition there. I mean this equation there, and collect the dv by dz term. So that's just going to come with this coefficient. That's that. But then there is also the dv by dz which comes from the second derivative, and that we said is 2r, 2s, 2t with these poles. So it is just adding up this 2r. You see here, 2r, 2s, and 2t. Okay. And now you see that by doing this, we are basically redefining the parameters alpha prime, beta prime, etc. Okay. So that's one thing. And now finally the last term, which is a mess, but we have to, yeah. I mean, so let's see. So what is going to happen here? Okay. So again, from the u, I mean that prefactor again comes out. So I have gotten rid of the prefactor. So here you get 1 over z minus z1, z minus z2, z minus z3 times this whole thing. So here there are many pieces, unfortunately. Plus, okay, I mean all of these terms. But then I have to also take care of the remaining pieces. It requires some algebra. Maybe I should just leave it to you to try that. I mean, at home you can. Okay, this whole thing is multiplying v, but there are also several other pieces which are non-derivative terms. For example, from this term you get that, right? I mean this bracket times this whole thing. So it's a mess. And then from here again there are non-derivative pieces. This term as well as this square term. So you see there are a huge number of terms. I'm not going to do that. It's going to take me half an hour to write them down. So this term plus, let me just write down this term, let's say term number 1. So plus term number 1 times all of this coefficient. I mean, this coefficient was what we called P, right? The original P. And then you have this term. So this is this term 2, let's say. So plus 2. 2 is this one here with a minus sign, and then plus that term, which is 1 square. Right? The first term is just that bracket, and this last term is the square of that bracket. So all of this thing is multiplying V. This whole thing. Okay. Now, yeah, it's a mess, but after doing a lot of algebra, you will find that it again reduces to the same form, except you see alpha gets finally what happens is that alpha is replaced by alpha minus r, and alpha prime replaced by alpha prime minus r. Huh? You see that's if you just replace alpha minus r is call it new alpha. Huh? And same thing with the beta replaced by beta minus s, beta prime replaced by beta prime minus s, etc. Okay, and similarly gamma replaced by gamma minus t, as you can read off from here. Huh? It is quite amazing that when you add up all these horrible looking terms, that's all it does. It just replaces alpha prime by. It's I mean you try to do that. I mean it's just to convince yourself. So what is upshot then? Upshot is that by doing such a redefinition, u equal to that prefactor, this prefactor times v, what we have done is we have obtained a differential equation for v where these parameters are changed, right? In a not in a definite way. You see, both alpha and alpha prime are shifted by the same amount. Both beta and beta prime are shifted by the same amount, and gamma prime are also shifted by the same amount. But remember, alpha prime, I mean this alpha and beta satisfied a constraint, right? The constraint was alpha plus alpha prime plus beta prime plus gamma prime was equal to 1, I think, right? 1. But now if I shift this, what happens? You see, what we are saying is that I'm going to shift by this way, r, s, and t. If I shift like that, then the left-hand side gets shifted by minus 2 times r plus s plus t. But right-hand side, nothing happens. So this will make sense only if r plus s plus t equal to 0. So that's one constraint. Okay. So when I make that shift, see, the left-hand side will get shifted by something, I mean 2 times that, r plus s plus t, correct? So, but for consistency, it must be equal to 0, okay? R plus s plus t. Basically, what it is saying, r plus s plus t equal to 0, it says that the behavior of u and behavior of v at infinity is the same. You see, because at z goes to infinity, the leading power is z to the power of r plus s plus t. But if r plus s plus t is 0, we are saying that the behavior of u and leading behavior of u and v as z goes to infinity is the same. That's what it's saying. Okay, so that's it. I mean, you have to. This unfortunately, yeah, it's a mess. But yeah, it's a mess. But you can see this kind of structures which appears. Yeah, it's a lot of work though. Because, for example, if you look at this term, I times p, you'll have this times that, right? So you can start. No, you have to do a lot of algebra. I'm sorry. Yeah, you have to do a lot of algebra, because at this stage, you see, it's not even written in the. This has always 4 factors of this, right? Right. Here, for example, when I take the this term times that, it'll only have 2 factors, right? But then you have to rewrite it in some. So there's a lot of algebra required. But eventually, you'll be able to show that. Yeah, I mean, please try that. I mean, this will take me a long time, and it's not very enlightening to go through this. I mean, in some sense, you should not be surprised by this after all, right? because after all, I mean, I just want to, since I am not doing this complete calculation, I want to give you more plausibility reasons why this should be, you should expect that, right? Because after all, I mean, you see, so we are saying u is equal to z minus z1 to the power of r, z minus z2 to the power of s, z minus z3 to the power of t times v. Okay. Now we know that if I'm looking at this equation, suppose I expand around z1, z equal to z1. Okay. Then I know the u will have two solutions. One will go like z minus z1 to the power of r1 alpha, the roots of this indecent equations, and times the series, and the other will go like z minus z1 to the power of alpha prime, and again let's assume that alpha and alpha primes are all generic, so that the difference is never integer. Let's consider that. There are special cases where they're integers, but I'm just trying to give you a plausibility argument why you should expect that, right? So now if I substitute these ansatz for that, then you see v in the neighborhood of z1 will go like alpha minus r, correct? The leading behavior will be, because if I'm defining u equal to this thing and plug so this is supposed to be equal to that, right? Then how will the v behave near z1? The leading term will be this to the power of alpha minus r, because I will divide by that, no? Similarly, this second solution will be alpha prime minus r, right? And the same thing goes for the near z2. You'll have the solution will be z2 to the power of beta, and this to the power of beta prime. And again, we will have again this expansions, but shifted by s, beta minus s and beta prime minus s. So you should expect it. But okay, if you really want to convince yourself, you should check this to show that works. Okay, so the conclusion therefore is that, I mean, if you accept this, then the conclusion is that by such a transformation, you are actually shifting, I mean, you are changing the symbol, I mean, going from p, z1, z2, z3, alpha, alpha prime, beta, beta prime, gamma, gamma prime, z. You are shifting it to p, z1, I mean, shifting meaning, so let me write it like that. So this is equal to, what we are saying, this is equal to this factor z minus z1 to the r, z minus z2 to the power of s, z minus z3 to the power of t, times p of z1, z2, z3, alpha minus r, alpha minus r, alpha prime minus r, beta minus s, beta prime minus s, and gamma minus t, gamma prime minus t. Z. Where we have, of course, the condition that this condition that r plus s plus t is 0. Okay, that's the. So what this is telling me, that if I know the solutions for this equation, differential equation with these parameters inside, then I know the solution of this differential equation with these parameters, and just by multiply by this factor to that solution, I get the solution of this original equation. So this is what it means. So now you see I can shift these guys and make some convenient values. Just like before, by using the conformal transformations, we went to 0, infinity, and 1. Same way now I can change this by suitably choosing r, s, and t. I can fix some convenient values here. Now you can see how many parameters are there. To begin with, I had 6 parameters here: alpha, alpha prime, beta, beta prime, gamma, gamma prime. But now subject to one constraint. So actually there are 5 parameters there were to begin with, subject to this constraint, right? So there are 5 parameters here to begin with, and now I have the freedom to remove 2 of them, because not 3, there are only 2, because there's a constraint here, right? So I can use the two degrees of freedom here to remove out of 5 2 of them, so that finally you are left with just 3 parameters. Just 3 parameters will be left over finally. And similarly, Z1, Z2, Z3, we fix it to 0, 1, and infinity. So finally, the whole thing depends on only 3 parameters. The convenient choice, again, the standard choice for this is you choose this guy equal to 0. So I choose R equal to alpha. Okay, so this vanishes, and you choose also gamma equal to t. So t equal to gamma. That's it. So I can make 2 of them 0. And this one I make it to 0, infinity, and 1. This I did by the previous conformal transformation. Now I do so here also let me put here 0, infinity, and 1. And then I choose this thing. Then this will become 0. That will become 0. This will be something. This will be something. I mean some non-zero numbers here. But the sum of these numbers must be equal to 1, right? So then I can parameterize. So what happened? So I will write this as P. I mean this part, this P of 0, infinity, 1, and this one I made 0. That one I made 0. Then this will be some number, right? Some complex number in general. I just call that as A. Okay. I mean this is some complex number. I just give it. I call it A, small a. And this number I call small b. This number I call 1 minus c. I mean this is just a convention. I mean this is the way somehow, but isn't okay. So you see, I made this and that 0. Now I have 4 numbers here, but there is one constraint that the sum of these 4 numbers is equal to 1, right? So really only there are 3, right? So I just call one of them as A, other as B, and this one I call 1 minus C. Okay. Then what is the last one? The sum of these must be equal to 1. So the last must be C minus A minus B, right? So this is a standard parameterization. Okay. Okay. So this is by choosing R equal to alpha and T equal to gamma in this. But you see, S is not free anymore because R plus S plus T is 0. So once I choose R equal to alpha and T equal to gamma, S equal to minus alpha minus gamma. Yeah. Okay. So this is the standard thing, and now we can just write down the differential equation for this choice, and you will see that that equation looks much simpler than this horrible looking expression. Okay. So let's write down for this choice. So we have d2 u over dz2 plus, now you see alpha is 0, alpha prime is 1 minus c. So if you plug that in here, this becomes c, right? Alpha is 0 and alpha prime is 1 minus c. So this becomes c. C divided by z minus z1. Z1 is 0, so it's simply z. Z2 is infinity, so I can forget that. I mean, this becomes 0. And gamma, so gamma is 0 and gamma prime is that. So you get here 1 minus c plus a plus b divided by z minus 1. Okay, that thing times du by dz. And now let's look at this piece. So here again, see, since z2 is infinity, I have to just look at, these factors I can cancel. So first term gives me z1 minus z3 is simply minus 1, right? z1 is 0 and z3 is z3 is 1, so it's minus 1 divided by z square, because z1 is that, z square, and z minus 1, okay, times alpha prime, but alpha is 0, so that drops out. Oh, actually alpha is 0, so I don't need to worry about it. Yeah, in fact, these two terms are already 0 because alpha and gamma are 0. So I just need to look at one term, that's all. Okay, so this is beta times beta prime, which is A times B. And now let's look at, so there is one Z2 here, and there are these two Z2s here, and there's one Z2, one Z2, so that all cancels out. At Z2 goes to infinity limit. So you are left with simply Z minus Z1 times Z minus Z3, which is simply Z times Z minus 1. That's it, times V, times U. So you see, the equation looks much simpler. But the point is that this is the sufficiently general, because once you know the solution of this, you can find a solution for any arbitrary parameters by these transformations. And conformal transformations, you can make it any point Z1, Z2, Z3. So that is all. If you know the solution of this, then you can find the solution of anything. This is this idea. So we can again further simplify this. Let's multiply by, okay. So let me multiply, okay, let me put here minus sign and make it 1 minus Z. Okay, here also I put a minus sign and 1 minus Z. And now multiply the entire equation by Z times 1 minus Z. So you see you get Z 1 minus Z d2u by dz2. And here, if I take out Z 1 minus Z as a common factor, you get, is that correct? What did I do? Minus C. So what is happening is C times, so plus C times 1 minus Z minus 1 minus C plus A plus B times Z. This whole thing times du by dz, and then finally simply minus AB u. Yes, I think this you should be able to simplify that. So you see this is a linear term in Z. So if you look at the coefficient of Z, it is Z times, okay, first look at the coefficient of 1. So that is C, right? And then the coefficient of Z, you get here minus C and minus minus plus C, so that cancels. So I can take out minus here. So yeah, correct. 1 plus A plus B times Z. That's it. So it's a very simple looking equation. So just write this down again here. So the equation is finally this Z times 1 minus Z d2u by dz2 plus C minus 1 plus A plus B Z du by dz minus AB u equal to 0. So this is the hypergeometric equation with the parameters A, B, and C. Three parameters A, B, C. These are now completely unconstrained. A, B, C could be anything, because we have used all the constraints already. This is the final equation, and maybe I should stop here.